Hi guys, welcome to GTN ABAQUS Learning. In the last session, we looked at a truss and we modeled it in ABAQUS and found out that the results from the ABAQUS and from the theoretical calculations were the same. Now in ABAQUS, you can model the truss in a different way as well. For example, if you're going to model this, we can create a part 2D wire. Let's name it truss. We can make this as 1000. I can get another one which is a vertical element, make it 1000, and then we can join this. So this is our truss. We can create our material as well. While making sections, go to beam and you can select truss. And we can make this one 600 millimeters square. Again, we have to make another section which is truss 2, which is a truss. So change the area into 600 root 2, that is 848.52 millimeters square. Say OK, and then you can go to part again, go to truss. While assigning the section, you can select this two, as these two have a cross-sectional area of 600 millimeters square. And again, you can select this part and you can select truss 2, which has an area of 848.52 millimeters square. Done. Now this is your truss. Now you can go to assembly. Okay, and now you can put your boundary conditions, forces, and you can see it deform. The region I showed it differently last time. I wanted to show the importance of connectors there. Here, these points are automatically assigned as hinges, like we did last time. So for today, we'll be looking into beams. Let us say we have a beam like this, in which the end nodes, this one and this one, have 2 degrees of freedom. One is vertical, other one is rotational. Here also you have vertical and other one is rotational. Let this be node 1 at A and let this be node 2 at B. The reason why we are not considering the axial deformation as its degree of freedom, because it is generally negligible, and we tend to make our solving process as easy and straightforward as possible, making some valid assumptions. We all know that the stiffness of the beam is given by this equation. So we'll be using this matrix in order to solve a beam with different boundary conditions and different loading scenarios. Solving means we tend to find its displacements and reaction forces here. In ABAQUS or in finite element analysis, it will be difficult to obtain the bending moment diagram here. Generally, we'll get stresses, and these stresses have to be modified using certain equations to obtain your bending moment diagram or shear force diagram. We'll also learn how to do that using the beam bending equation. Today we'll be looking at a propped cantilever beam. It has a roller here, and at the end, let's say we have a spring like this. Let the length of the first half be 3 meters and the second half also be 3 meters. Let us say that our spring constant is 200 Newton per mm. and we are applying a load which is a concentrated load here. Let it be 50 kilonewtons. Now given that we have our Young's modulus as 210 GPa and moment of inertia as 2 into 10 to the power 8 millimeter 4. So given all these conditions, we are asked to find the reactions and displacements at these nodal points. Let's go into the procedure. First, let us divide the beam into two elements. Let this one be the first element and this one as the second element. Now we can label our nodes as well, and we'll have 2 degrees of freedom at each node. As you can see here, we also have this spring, so we can label one more node here. Let this node be 4, and we'll have 1 degree of freedom for this one as vertical, which can be equal to U4y. Now for this beam, we have to form our local and global matrices. To find the local stiffness matrices for each element, we can use this matrix for each of these elements, whereas for the spring we have to use a different matrix which is similar to the equation for axial rod. This matrix can be easily derived, as you have already done in our first session where we talked about the springs in series. In the beginning of our second session, we learned how to directly get the stiffness matrix by restricting or constraining degrees of freedom and then applying a unit displacement at certain points. So we can go back to our session 1 and 2 to find out how we can obtain this matrix. Here also we can use our global direct technique to find our global matrix. So to do that, we redraw our beam. If you don't want to form local matrices, then this method can come in handy. Now in total we have 7 degrees of freedom, so what we'll write here is a 7 by 7 matrix. This first row means when you restrict our other degrees of freedom, which are this one, when you fix this and this, and we apply a unit upward displacement, then we have to find what are the reactions here, here, and here, and put them accordingly. So for this case, to produce a unit displacement force in this length of the beam, this will be equal to this value here, which is corresponding to U1. Therefore, this will come out to be 12. Let me take EI by L cube as a common outside, so it is easy to write. So this will be 12 EI by L cube. And theta 1, which is this, since we are moving this one, we'll be restraining our movement here and find out what force you get. So for this one, which will be equal to 6 EI by L square, therefore it will be 6L. Here similarly it will be, reaction force will be minus 12 and theta 2 will be 6L. Now from here to here, at the degrees of freedom U3y, theta 3 and U4y, there won't be any force transfer, as every reactions to this action will occur at this point, and this point will have nothing to be loaded. Therefore we will have these three values 0. If we look at the second row, this means that we fix these degrees of freedoms and we also fix our vertical. So this will be kind of a hinge where we'll apply unit rotation. To produce 1 unit rotation, we will have a force equal to 4 EI by L. So this will be 4 L square. It will produce a reaction force here, which will be equal to 6 L. And this one will be minus 6 L. And this one will be 2 L square. And again, the force won't transfer to these points, so it will be 0. Now, when you look into a third row means that we have to fix these degrees of freedoms, and we have to apply a vertical displacement of 1 unit, and we have to restrict our rotation as well. And now we have to find what will be our required force to produce a unit displacement which bends this beam, something like this. When you apply a vertical displacement of 1 unit, this will require a force of 12 for this beam to move like this, and 12 for this beam to move like this. So if you add it up, it will equal to 24 EI by L cube. Therefore, this value is 24 EI by L cube, because we are displacing two beams of same length by 1 unit displacement. And for the rotation, when displacing this beam and this beam, the forces will be equal and opposite, so they will just cancel each other. Therefore, there won't be any reaction here, so it will be equal to 0. Now for U3, which will be the reaction force here, which will be equal to minus 12 EI by L cube. And for theta 3, because of this one, we'll have 6L, and since every force is taken by this restrained degrees of freedom, no force will transfer at this point, so it will be equal to 0. And for this one, you can just write here minus 12 and 6L for the symmetry, because this matrix has to be symmetric, which means that we don't really have to find these values. If we are sure that these values are correct, we can just find the values right to our diagonals, and these ones can be added later. For our fourth row, in which we are focusing on degree of freedom theta 2, which is rotation at this point, we'll be restricting our vertical displacement but applying a unit rotation. So this will require a force here to rotate this point by unit radian, and consequently will produce reaction forces here and here. So when you rotate this one, which is our fourth degree of freedom in our standard equation or standard matrix, which corresponds to our this value here, since we are rotating two beams in the same direction, this will produce cumulative force that will be around 8 EI by L, which will equal to 8 L square here. And then this will produce a reaction force here and here. Now for this point, it will be around minus 6L. Again, it will produce a reaction moment here, which will be equal to 2 EI by L, which equal to 2L square. Now there won't be any force transferring here. Now you can just copy these values right here. So this will be equal to 6L. Now let's move into another degree of freedom, which is degree of freedom 3y. That is the vertical displacement at this point here. So for this one, we will be fixing this. We'll be restricting rotational motion here by spring, which has infinite spring constant value. We'll apply unit displacement here as 1. Now this will deform the beam like this. To deform the beam like this, it will require 12 EI by L cube. But since we also have this stiffness here, that equals to k, we have to add that up. So for our u3y, it will be 12 plus k. Now since we have taken ei by l cube common, this will be equal to k l square by ei, because when you multiply this and this, it will cancel out these two values and we will have only k remaining. And again, it will produce a rotation moment here, reaction, which will be equal to minus 6L. And here it will produce a reaction force which will be acting downwards, which will be equal to minus k. Now this will be equal to minus kl square by ei. For theta 3, we will be hinging this point. We won't allow any vertical motion, and we will release the rotational degree of freedom and apply unit rotation here. So because of this beam will deform like this. Now this will require a force of 4 ei by l, that will be equal to 4 l square, and it will produce zero reaction here. And for our final degree of freedom, we'll be fixing this and providing a vertical displacement here upwards by unit, which will require a force of k, which is equal to spring constant. Now this will be equal to kl square by ei. Now this matrix is generally symmetric, so we can just copy our values here. This will be equal to 0, 0, 0. This should be equal to minus 6L, and this will be equal to 2L square, then 0, 0, 0. This will be equal to 0, minus 12, 6L, 0. This equals to minus 6L, 2L square, 0. This will be equal to minus 6L and minus KL square by EI. Please make sure that this matrix is symmetric. So now we have our global stiffness matrix, which equals to Kg. So you can determine this matrix by this process as well, but it is generally safer if you go by the process of finding the local matrices first and then combining them, rather than directly finding the global matrix. If you are confident, then you can directly derive your global matrix like this. Now we have our well-known equilibrium equation, which is, so these forces correspond to forces occurring at these degrees of freedom here, which are 7 of them, and these ones relate to the displacement that will occur at those degrees of freedoms. Now you can substitute your boundary conditions. So your boundary conditions here will be u1 equals to 0, theta 1 equals to 0, u2 equals to 0, and u4 equals to 0. When you check here, this one is 0, this one is 0, this one 0, u2y 0, 0, u3y, and u4y 0. We are left with this portion here. Copy this portion down and put the values in, which will be multiplied by theta 2, u3y, and theta 3, which will be equal to our forces. In these 3 degrees of freedom, at theta 2, we have no force applied. Therefore, here the force will be 0. For u3y, we have 50 kilonewton force acting downwards. So we'll write here minus 50. And at theta 3 also we have 0. Now we can solve this equation. Now when you substitute your values here and solve it, you'll obtain, so this will be your solution. You require displacements and rotations at the degrees of freedom. Now to find our reaction forces, we substitute these values back into this equation here and obtain our forces. So when you do that, you'll obtain your forces as, so these will be your reaction forces here. Now when you draw your solution, we'll have 70, 69.7, 116.4, 50. Now to find the force due to the spring, we have our displacement here as say minus 17.4 millimeter, which is occurring at this point here. So because of this, we have to multiply our 17.4 into 200. This will give us a force of 3.48 kilonewtons. Now these all values are negative. Since our convention is anti-clockwise positive, this one and this one turned out to clockwise. Our beam is going to bend something like this, where this is our clockwise angle, theta, and there will be another angle here which will be equal to theta 3. This is u3y. Now we'll model this beam in ABAQUS and see what we get. So to model a beam like this, first we have to create our part. So go to parts, 2D deformable wire. You can keep this as 6000. We have to make a long beam here. Total length is 6 meters. That's done. Now create our materials. Steel, which has elastic property with Young's modulus 210,000. We can assume Poisson's ratio to be 0.3. Then we have to make our profile. We can make a rectangular profile here. Since we are given moment of inertia as 2 into 10 to the power 8 millimeter to the power 4, we have to find a dimension for which our moment of inertia will be equal to this. So we all know the equation for moment of inertia is b d cube by 12 if we have a rectangular section with depth d and width b. We can use Excel. The way we do is we can assume one value here. We can assume say 40 here. Now we have to solve this moment of inertia to be equal to 2 into 10 to the power 8. For this we go to data, solver. So we select our target cell, which is this one. We set this value to value of 2 into 10 to the power 8. That's what we want to solve it for. By changing variable cells, we want to change this variable keeping this 100. So when you click solve, you'll see that it returns the value of 288.44, which gives moment of inertia as you require. So you can say okay, our width will be 100 and our depth will be 288.45. So we go to ABAQUS, we can write 100 and then 288.45. OK, now you will have your profile. Now let's create our section. Our section will be beam. Go to beam again, continue, and then you can select your profile 1. You can assume this to be 0.3. Say OK. Now we have created our section. Now we go to our part and assign our section. So you can select all of the beam, say done, select section 1, say OK. Now we have to assign its orientation. So go to assign beam section orientation, make sure you select all of it, say done, and hit enter, say OK. That's it. And then you have to go to material orientation, select all of it, click done, use default, say OK. Now you have your section orientation and material orientation. As you see in our problem that we have a roller right at the center here. In ABAQUS, when you take this beam directly assembly, you might not be able to select the center to assign its boundary condition. If you have a roller here, somewhere here, let's say at a distance of like 5 meters, then we have to create so that we can assign our boundary condition. We go to tools, partition, go to edge, and then select midpoint or datum point. So you can select this point and say create partition. That's it. Now let us go to our assembly. So you bring our beam here, say OK. Let's move this beam at the center of space. Here we have to assign. To do that, go to assembly and then go to engineering features, go to springs and dashboard. Now this time we won't be connecting 2 points. What we'll be doing is that we'll be connecting the spring here to the ground. If you look into our problem here, see the spring or is fixed somewhere. To form a spring like this, we have to select connect points to ground. So click continue and we select this point here, say done. Now we assign our spring stiffness as 200 Newton per millimeter. Now we have to select at which degree of freedom we want to assign our spring. So for this case it is vertical, so that is 2. So select 2, say OK. Now you have your spring. Let us create our step, which will be static general. Continue, make it as high as possible. This one 0.001, as low as possible. OK. Now go to our field output, what we want to see. So click OK. Now here we have to specify load. So go to loads, concentrated force, and at this point we have 50 kilonewton force acting downwards. So this is 0, this is minus 50,000, that's 50 kilonewtons. So that's OK. Now we have our load assigned. Now go to our boundary conditions. So for this point, which is fixed, you can just click, select it, click done, and then incastrate. That means it is fixed. Now for the roller, select displacement and rotation, select this point here, done. We will be allowing motion here, but we'll be restricting this one. So say OK. Now we have our roller here, we have force here, we have spring attached already. Now one thing is that we have to mesh our beam. So you go to mesh, let's go to part, that's our part 1. You can seed it. Let's seed it by say 100 millimeter. Apply, OK. Mesh it, mesh part, yes, and then go to assembly, go to mesh. Now you can see your mesh part in the assembly. Now I believe that's it. Now you can save your model. Let's us create a job here. This is beam. In this space here, you can change your memory allocation, or if you have more processes, you can increase your processes to say 4. Now this is a quad core computer, that's why I can select up to 4. Let's select it up to 4. Now this will increase our speed. Now say OK. Now let us submit this one. Submit. You can monitor it. That's it. Done. Really quick. Dismiss. Now let's see our results. Select your ODB file, and we want to see our reaction forces. So click here, go to RF. You'll see reaction forces occurring here as well. So we click on this one to see our values. Let's look at our vertical reaction forces. Yes, this is it. Now for the roller case, this degree of freedom, we obtain it as this as 69.2 kilonewtons. So let's look at our solution here. This is 116.4 and this is 70. In ABAQUS we get 69.2 and 116, which is very close. These are rounded values. To see the exact value, go to tools, you can go to query and go to prop values. You can select on nodes, and I can select this point right here. You can just click on it. You will see it is 115.7 here, and you can select this end as well, which is 69.2 kilonewtons. Now you won't have any reaction forces elsewhere. Now we can go to our, just bring it down. Now you can just go to our moments if there is. So you can go to primary. That's our moment. Yes. Section should produce a reaction moment here. Now this is equal to 6.825 times 10 to the power 7. Now this is a Newton millimeters. Now when you convert that to kilonewton meter, we have to divide this by 10 to the power 6. So this equals to minus 68.25. Now let's look at our solution, which is around 69.7. Now that is close enough. Now let's check our displacements here. So we can just go to tools, query as well, go to prop values, select nodes. You can select displacement as U for vertical. So 0 here, 0 here, this one here, we won't be able to see it, would we? So this one nearly is equals to 16 point minus 16.9, that's nearly equals to 17. At our solution we have 17.4. Let's look at our rotations. For that we have to go to UR3 and you can click on this point and this point here. Sorry, it's close to it. This point. We have our rotational values as 0.00254 radians. This is correct. This is correct. And let's look at our third, which is around 0.0075. Let's look at our solution, that is also 0.0075. In this beam, we won't be able to find our bending moments. Now, since we have our reactions, we can obtain our bending moment by using those reaction forces. Or if you want to find our reaction forces directly from here, but first find our stresses. Let's find our stress. This is our stress. Let's want to find our bending moment around, somewhere around here. So let's go to tools, query, go to prop values. I'll select this one, which is misses. Let's go to max principle. You can just select here. Now this equals to 25.65. 25.65. I'll write that value here. Sigma 25.65 Newton per millimeter square. Now to find our moment at that location, now that location is, let's go to distance, let's find out. Click here, it's this one, and let's go to probability. Okay, yeah, that is it. So the distance here is 1.5 meters right at the center. So for this case, if you want to find our moment, we have to use this ratio equals to this ratio. Now if we equate it, we can write moment m equals to sigma times I by y. Let us substitute the values. Sigma will be 25.65. Our I is 2 into 10 to the power 8, and y, meaning of y is if you have a section like this and you have your mean line here, or that is our centroidal axis, and this is your extreme fiber here. It is a distance between your centroidal axis and the extreme fiber here. So for this case, this is d, which is equals to 288.5. that will be half of it, so it will be equals to 288.5 divided by 2. Let's solve this. So that will be 35.56 kilonewton meter. So this will be our moment at the midpoint of the first element right here. Now the other way to find our moment is to use our reactions to obtain our moment at the center. So let's find this out. So this is 1.5. So the moment at this point will be equal to 70 times 1.5 minus 69.7. So this will be equal to 35.3 kilonewton meter. So you can use this process to find your moment at this point, or you can find your stresses using ABAQUS and determine your moment here with this equation. This is how you solve or you model your beam and find your reaction forces, find your moments, stresses in a beam. So today we learned how to form the global matrix directly by looking at your system. We solved our beam with a spring at the end, and we obtained our reaction forces and our bending moments. And we modeled this in ABAQUS and obtained similar results. And to find the bending moments, we used our beam bending equation, and we used our simple equation to find a moment here. In the next session, we will learn about frames. We'll try to model some frames and solve them. Now solving frames will be similar to beams. Therefore, we'll be looking at some complex frames which have inclined columns or inclined beams, where you have to rotate our reference axis in ABAQUS to solve them. Thank you for watching till the end. Please comment, share, and subscribe to this channel. Thank you.